Let's see if we can. Let's see, did I remember to share screen? Share screen. Let's go. Well, thank you everybody for coming today. I did say I was going to talk about Greenland, but I thought I'd start with Antarctica just because the ice sheets are so connected. And some of this is going to be a reflection on both what we know about the changing ice sheets, what we don't know, and then how we think about working with communities and how we share our knowledge, and how do we think more about moving our science from being useful to actually being used. So with that as sort of a overview, first of all, I want to, thank all the people who've helped me with this science that I'm going to show you. There are people from around the world, people from Lamont, all sorts of different people and funding agencies have supported this work. So my heartfelt thanks to them all. And I'm really just here as a conveyor of stories, but really I'm showing the work of many, many other people. And I hope to remember to point out the important collaborations. I always like to start out by remembering, that we have 2 poles and 3 ice sheets. Each one is very different, has a very different character. Greenland in the north sort of sticks down into the Atlantic, sees the same weather we do. My friends in Greenland see the weather we see a couple days after we do often. If we are having a storm now, they're going to see a storm soon. Whereas Antarctica really makes its own, so isolated, makes its own weather and has been isolated for a long time. So I always just like to stand back and say, remember that. And it really is this interactive system that we have to figure out how to understand, that we often focus on one piece of it, as we go forward. But if we're going to understand how sea level is going to change, we have to understand the entire ice system, but also the underlying rock, ocean, and atmosphere. And that's a tune I've been playing for a long time, that we need to look at that interaction between the ice and the ocean. But increasingly, I think the ice and the bedrock, but increasingly it's becoming clear that we need to look at the entire integrated system. And I can remember when sea ice was really the most emblematic and most argued about piece of change in the cryosphere. We now know that it's really clearly changed a lot in the last decades. But I can remember standing in Lamont Hall about 2003, so right here where it curves over, and listening to the community argue about whether or not we were seeing interannual variability or if we were moving into a really dramatic change. And I can remember walking out of the room and saying, we don't know, because in the early 2000s, we really didn't have enough of a signal. And it was one of those arguments that was not clear yet, but now it's really clear that we as humans are impacting that ice system, as well as the other ones, the glaciers in the north, the glaciers in the south, and those giant conveyor belts in Greenland. And even in this picture, which I often show just to remind people what a glacier looks like, this is looking out the window of the ice pod, looking forward on a C-130. And even if you look on the left of this image, you can see the drawdown signal. You can see how that strip of white before you get to the green, that is the signature of how much already the ice sheets have drawn down and dropped. So it's really everywhere we look. And I never give a talk without going through this evidence because I just think it's so compelling and I think we should all be able to articulate it. You can ask me to talk about sunken ships on the Hudson River and I'll slip this into the talk because I feel like that's one of the things we need to work on when we communicate with our community about science is we need to put in the strong evidence of change that underpins our work. We need to make sure that they can understand it and that they know how robust the evidence is. So I always like to start with, there are 3 signals of changing ice. It's moving faster, it's getting lower, and it's losing mass. And that those are 3 independent lines of evidence made from different measurements. And then this is just one of my favorite animations that shows how in the Pine Island area, places where many people on this call are working, is that the ice sheet velocity has doubled over a course of a decade. And in the same time, we've seen that ice sheet elevation drop by up to, in the ICEAT time period, up to 60 meters. And we've seen that continuing to drop. And again, these are places, where the names are so familiar, Pine Island and Thwaites, places that are a focus of much activity going on. And then really there's one other signal. Not only do we see that the ice is getting lower and going faster, but we also see that it's losing mass. And that's what that big red blob developing in the same part of Antarctica is, the mass loss. So again, talking to our community, our communities, not our science communities, but the communities we live in, it's just so powerful to share that we have 3 independent lines of evidence, 3 measurements that tell us the same thing, that the ice sheets are losing mass, and they're losing mass in a way that's faster than we've ever thought was possible. The first paper I ever published on the West Antarctic ice sheet, Charlie Bentley made us take out lines in the review process that talked about rapid change. It was just in 1990, it was still inconceivable that we could see rapid ice sheet change, and the community wasn't willing to see that published in places like Nature. Oh, but you can see that still there's much left to understand. As while we're seeing a lot of change in the peninsula and in the West Antarctic, the Pine Island Thwaites region, there are parts of Antarctica, particularly up in East Antarctica, where we actually are seeing that signal of more snow. We are seeing what it has been predicted, that there will be more snowfall. And that's what the blue is showing, places where mass gain is happening. But that certainly is, the amount of new snow falling is overwhelmed by what's flowing into the ocean. So, what does that look like in the, at Lamont? One of the beauties is we always look at sort of how things fit in the long time frame. And this is the weather for the climate for the last 15 million years. And this is a figure that Barabel Hornish helped me put together for a review article in Science earlier this year, really looking to see how, we have been living on this 50 million year trend towards colder temperatures. And with that, somewhere around 34 million years, we went from an unglaciated to a glaciated Antarctica. And you can see that drop in both temperature and CO2 that seemed to be what triggered the onset of glaciation on the high parts of East Antarctica, particularly the Gimpertz Mountains. And then you can see that over time, we've moved to a period where first we had glaciation intermittently on West Antarctica, and then we've moved into this interaction between a glacial maximum in Antarctica, where you have the ice going out to the continental margins, or you have marine ice sheet collapse. So that's sort of been the history of the past 50 million years of the ice sheet. And what does it look like when you look at it in cross sections? And you have to remember that, I guess, when
Some of the people on this call were graduate students or were just starting to think about ice. We still did not know how much ice was in Antarctica. That these fundamental measurements you see on the top, that the ice is up to 4 kilometers thick, were something that we learned in 1958 due to the International Polar Year. Until then, we thought that the ice in Antarctica was a relatively thin film over high topography. But we now know that East Antarctica is up to 4 kilometers thick, but it covers rich terrain from the Gamburtsev Mountains to Lake Vostok, to parts of it where it actually is a marine ice sheet, where the bottom is below sea level, which is what most of West Antarctica is. And you can see that down here in the lower right. You can see that the blue parts are parts of Antarctica that are currently below sea level, and the brown is above sea level. So you can see that the pieces are below sea level are the ones that we now have come to understand that are more susceptible to change in ocean temperatures as well as changing atmospheric conditions. So these are what we call the marine ice sheet and the ones that we worry about most. Just because the other thing I always love to look at in a talk is really looking at how old is the ice sheet. You know, we often just think of, we think that we've come to understand from the ice cores how old the ice can be, but we don't actually think about how old those ice sheets are. West Antarctica, the marine ice, we are pretty sure that we see ice up to 68,000 years at the base, whereas in East Antarctica, we have ice that's definitely over 700,000. This is Vostok, where the bottom is 420,000 years. But you can see that much of the ice sheet is pretty old. As I like to say, much of the ice in Antarctica, the base isn't, in East Antarctica in particular, isn't even aware of the end of the last ice age, because that thermal pulse hasn't moved its way through the ice sheet yet. How do we know there's ice? There's lakes underneath the ice. It really is because of the surface topography. I showed you radar, but the fundamental knowledge that came out of that there is water underneath the ice sheets really came from the fact that where ice floats, it's very flat. Where it's on top of topography, it's rough. You know, these two extreme end members of thinking whether or not you're skiing on a glacier or whether you're skiing on a lake. Really, when you go look at the ice surface, you can see that Lake Vostok is flat. It's the same size as the state of New Jersey, but it is 4 kilometers of ice. And you can see the parts that are not where there's water is, again, you can see other flat areas over here, but it's relatively rough where the ice is grounded. And this is the beautiful image that, again, really allowed us to say that Lake Vostok was a lake, remembering that it was first discovered in the International Polar Year, but it was misinterpreted as a pile of sediment underneath the ice sheet. So that's what Vostok looks like, with the ice flowing over, and where we first began to have this concept that the ice sheet could interact with the water underneath, because when they were drilling for the climate record, when they got to the bottom, they found that there was ice that was not ice that had fallen as snow, but it was actually ice that had refrozen onto the base of the ice sheet as the ice flowed over the lake. You actually have ice added to the base of the ice sheet. You know it's didn't fall as snow because you have different acidity, you have giant crystals, and you have no bubbles left in the ice because they've all they're not reattached in the refreezing process. So there are other ways we can map water. This is a radar image. You can see bright water underneath the ice sheet. And it turns out there are water systems beneath much of Antarctica, and mountains. And just because this is one of my favorite stories, I thought I would just share it here, is that during the IPY, in that terrible introduction, was what we were planning to do. And we did actually manage to get to the Gamburtsev Mountains.
and we did say we were going to look at water systems. You can see that it's not that far from Vostok, but this area is about the size of California. This is what it looks like. This is what it looks like underneath the ice sheet, where the surface contour shows what the top of the ice sheet looks like, and underneath you actually see the mountains. In the valleys, there's water. Looks like that. You've already seen that. Ice layers, mountains, water. But what was really remarkable was the fact that there was really water in each one of those valleys. Wherever you see a green dot, you see water. And what we hadn't expected was to start to understand how the plumbing works, and seeing that the water actually gets driven uphill because of the way that the ice is putting more pressure on the downhill parts of the river valleys and less pressure at the uphill parts, and the water actually ends up being driven uphill. One of these remarkable moments in science where you start to see things in the field. You aren't really supposed to be doing science, but even in the field, you could see that there was something that looked like what was going on in Vostok. You have mountains, and you have things that looked like clouds, or weird things that are not supposed to be at the base of the ice sheet. So here are mountains, here's the layers you're used to seeing, but here's something that looks like a blob, or a dental x-ray is what Michael Studner thought, or something else, a strong offline reflector was what Beth saw it. But what was remarkable is you could actually see it looked just like Vostok. You could see material being added back onto the base of the ice sheet as the ice flowed. So really just wanted to show this as an example of how there's much we don't understand about how ice sheets work. Those structures I showed you came off of the end of each of those large valleys. And again, they're directly connected with the water system. So they're places that you see that the water flows uphill and you're suddenly modifying the ice sheet. So just a little bit about how there's still so much to discover even about the interior of the ice sheet. So how does that relate? And so I thought I would just step through now, what it is we know about Antarctica, how it's changing, and what are some of the outstanding problems. And I thought I would just step through some of the nice imagery that was put together as part of this series of review articles on Antarctica earlier this year. And we certainly know that the classic signal of changing ice in Antarctica came from the collapse of the Larsen ice shelves, particularly Larsen B, that the sort of classic picture of water atop of ice sheets. This is again showing how this is the region that's sped up. You have mass loss. So what do or don't we know? Well, some of the unknowns that we don't really know that were highlighted here, in essence, the classic retrograde slope, the fact that if you pull an ice sheet back to where it's getting deeper and deeper, this is considered the marine ice sheet instability. And that's considered to be a runaway. We don't actually understand what the role of rough topography and basal conditions here. It's thought to be driven by heat coming in the deep ocean and attacking the grounding line, or by having the loss of one of these ice shelves. Similarly, the other concept that's out there is a cliff failure, where you would have a hydrofracture or causing an ice shelf to collapse. And again, once you lose the ice shelf, you end up with large cliffs, and the cliffs are fundamentally unstable because you can only support so tall of a cliff. So we have models out there, and this is one of the things I'm going to come back to, is how we communicate this. This was in Frank and Mathieu's paper, basically showing, what the range of projections we have out there, both for 2100 or 2300, and then the plots of showing what's happening. What you first realize is that the challenge we have when communities ask us what they should be planning for, it's very clear why. If they just read the literature, there's tremendous difference. This is DeConto and Poller, who have the very high end numbers. And this is with the ice cliff. And then you have more subdued lower numbers that don't include those processes. So again, you can see that we as a community we as an ice sheet community cannot provide robust answers next yet to what communities should be planning for. Again, just getting back to how do we see these? I've managed to put myself on top of my figures so I can't see them. Let's see. So you can either have two different types of ice shelves. One is kind of like the Ross, where it doesn't seem like the warming ocean water can get to that grounding line. The other ones are more like that Pine Island Thwaites region, where you actually can see warming water getting into the cavity. Again, the big ice shelves like Ross and Filshner-Ronne being considered these cold water cavities, and these warm water cavities are what you see along the coast where we see so much change. What's driving it? Are there teleconnections? The real current understanding is, and again, this is from Dave Holland's paper in that same series, is that it does appear that there are, this is part of a long-term trend, that it's driven by connections with the tropics, that we are in fact looking at a tightly connected planet, and that changes in the tropics are in fact driving the winds that are driving that warm water up. And this just again gives you a long-term sense of what the long-term trend has been in the westerlies, which appear to be contributing strongly to that driving water up. So that's sort of just a background, but what are sort of the limits on, why is it that we are so challenged in terms of being able to give answers that planners can move forward on? I'm going to just suggest there's 4 things that I think we're still getting our hands around. Local processes, the fate of surface melt and its impact, how ice fractures, and the base of ice shelves. And just had to have some movie just to make sure people are awake. That's letting you know what a local process is. This is actually making so that was launching an airborne Alamo float, which is an airborne Argo, as part of the Rosetta project. And just what were the lessons that we learned from, surveying an entire cold, what you might think was a cold-based ice shelf, where it didn't seem like it was susceptible to change. What Kirsty Tinto, you may have heard her talk recently, was able to show, or you can go back and look at it. It's on the Lamont Colloquium website. She was able to show, as a result of this integrated work, that while we think of those cold ice shelves as being protected from the warming ocean, in fact, there are susceptibilities to change at the front at places that actually are relatively weak and are driven by local processes. This is just a cartoon that shows where we were able to observe high melt from local processes, things that we were able to observe in those CTDs that Dave Porter led deploying. So again, I think one of the things we need to do is both look at these systems as integrated systems, but recognize that we need to address local processes and not just global processes. Second, on the sort of outstanding questions, while the paradigm is that surface melt will collect in crevasses, cause hydrofracture, and cause the failure of ice shelves, it's very clear that that's a relatively narrow view of surface hydrology. Everything from, it's very clear that water can be transported off. This is a paper that we published in 2017 about waterfalls transporting water off the surface of ice shelves. Johnny Kingslake et al. Demonstrated that water can be transported in river and stream systems onto ice shelves. And more recently, Alex Bogosian is working on the concept that you can actually have surface rivers that insize and weaken ice shelves to the point that we're actually seeing fractures form along surface rivers. Again, pointing to there all sorts of processes that we're not including yet in our large-scale models, but can control both the failure of ice shelves and the eventual fate of the ice sheets. So another big outstanding question, I think Yao is on this call, is that understanding fractures really matters. Yao published this beautiful paper that linked both mapping fractures and parameterizing them this year, but that's the kind of work we need to do. We need to understand how the ice shelf, how ice fractures, and how we accurately represent that in models. And then the one other unknown I think we really haven't embraced yet, and this is something that Kirsty Tinto and Dave Porter and Atsumu Muto are moving forward on. It's how should we be thinking about the base of the ice sheets? We certainly in global climate models have vegetation classes, but we are still relatively simplistic in how we deal with the base of ice sheets. And I think the way I like to think about it is we might have a gradient that shows what the varying heat flow is. We might have something that's a little more rich that is a satellite-based heat flow. But in fact, really what's going on there is there's a geologically controlled distribution of heat and fault controlled. And really what we should be thinking about is how do we move forward with the concept of bed classes that would actually advance our parameterization of the base of ice sheets. So because that's, when you look at this model, which is back to that very high end projection of DeCanto and Pollard 2016, you can see some of the things that makes this ice sheet collapse in their modeled ice sheet collapse really rapidly, and provide those very high end projections that communities have moved forward on. Much of it is based on the concept that how ice fractures and where surface melt goes. So again, those are some of the big frontiers we need to look at, because providing our community this level of information is really insufficient. So I thought I would flip a little bit, because this is going to drive us towards the Greenland project, and something that I've reflected on is, with so many new unknowns, how do we connect with our communities? And I'm not talking about our intellectual communities, but the communities and the entities that need the information we're working on. How do we ensure that the science is not just useful, but used? And it's something that I feel very strongly about, because as I've had the fortune of traveling, I'm often surprised. Almost everywhere I go, yes, sea level's going up and people are worried about it. Whether it's here in New York, and we know that if you go down to the Battery and it's going up at about 3 millimeters a year. And this is just back to, it doesn't matter where we go, we find people are seeing that their cultural heritage is being impacted. So how do we communicate better? I found that one of the very powerful tools is actually to leverage the work that's out there in the National Climate Assessment, because what that has is it has very much localized issues of how climate change is occurring around the US. I've found it so I can now articulate to people that in terms that they can understand. I've tried very hard to get people to understand what sea level is by getting them to feel their legs and understand that's how much it's gone up since my grandmother was born. But I find it's much more powerful if you can talk about the warming temperatures, longer growing seasons, and the people are catching different fish. These are things, we don't often talk about as scientists, but things that people can relate to. And, there's the things that people have seen in their own experience. This is my experience of Hurricane Sandy. But, being able to explain to people that temperatures are changing, but they aren't changing the same everywhere. I was at an event just last week, I guess maybe it was 2 weeks ago, where Marilyn Raphael, who was giving the overarching introduction to climate, when she showed this, the climate activists who've been working in the South were suddenly so empowered because they realized they could talk differently to their communities because the temperature is not changing the same everywhere. That we're able to talk to people about how when their gardens are coming up is changing, that we're seeing a longer growing season everywhere. The first blooms are coming out so much earlier in much of the country. And then I actually just take the story back locally where I tell people, look, my daffodils come up sooner and I have basils on my pizza longer. Again, trying to connect to people because we need to have those narratives that allow us to answer that question of how can we get communities to listen. And then I think one of our challenges is how do we develop a methodology where we actually vet these numbers before communities start acting on them. Certainly in the medical field, there's a very clearly defined process before anyone will step forward and use a medical intervention most of the time. But we haven't really gotten that around our heads yet about how we use climate data when we talk to communities and how they act on it. And there's a lot of literature out there on how do we work with communities, whether it's indigenous knowledge or whether it's the Pope. It's just some of the things I find on my desk because I grapple with this a lot is how do we can move from the beauty of discovery, which I kind of shared with you, to actually the uncertainty in our data to making sure our data is useful. So that brings me to Greenland Rising, which is this is really the brainchild of Jackie Osterman and Kirsty Tinto. They're the ones who came up with this concept. It's a NSF-funded Navigating the New Arctic project where the goal was to link the natural environment, the social environment, and the built environment to, in essence, work with communities to understand how change was happening and how to better prepare for it. So, when we wrote the proposal, we had these three concepts that we would improve the modeling of the past, present, and future sea level rise or sea level fall. Remember, this is Greenland because of self-gravitation and isostatic rebound. Sea level is going to fall around Greenland, but in different ways. And what we were going to leverage was the concept that we could map the bathymetry around communities to be able to understand how that was going to impact both benthic habitats and infrastructure and working with communities. So that was the plan. And these are the 4 communities we were going to look at, or we are going to look at, where they have very different signals. And there's a rich history of GPS around Greenland. So we actually have measurements of how this northernmost town is going up 10 millimeters a year. Nuuk is the capital is only going up 3 millimeters a year. And you can read the numbers yourself. Asiat is going up 6 millimeters a year. And Tesselak is going up 7 millimeters a year. But then you can see each of them has very different projected sea level rises for 2100, ranging from, almost 3 meters fall to almost staying the same at Nook. So that was our concept. And the idea was we were going to install tide gauges, map benthic habitats, and improve this understanding of how sea level was going to fall over time, and really aiming to do it collaboratively. This is a picture of a program that Dave Porter and Margie Turin did in Kalorslack, that northernmost town, with Climate Center funding. And then this is installation of tide gauges, and that's the ship we're using for mapping. We did go to Greenland in January. Thank goodness. I think that's sort of step one in working with a community. And it's one of what my colleague who works on sea level in San Francisco has said, is that the most important thing to working with a community is to go in with a blank piece of paper and collaborate from there. And as opposed to going in with your preconceived notion that if you're going to work together and build solutions together, it's very important to go in with a blank piece of paper. So 7 of us went to Greenland in January and spent somewhere between a couple of days and a full week there. Here's Kirsty, Margie, and Dave at Culture Night. We were able to stay for, or they were able to stay for what's in essence the open house of Nook, which meant they had the opportunity to talk to 1,500 people, which is about a tenth of the population of Nook, about how the sea level's changing, what's underneath the ice sheet, and expose them to our program. We also spent time planning where we were going to survey and how we were going to do surveys. One of the remarkable things was during that meeting was I was able to go to I have a friend who he and his wife sailed his boat up the Hudson and stayed here in Nyack, and we had them over for paella. He gave me he carved this ptarmigan for me. And then, so when we were in Nook, he had Johnny, Jackie, and I over for dinner. And when he's a sailor, obviously that's why he was here. They were the first Greenlandic people to do a circumnavigation through the Northwest Passage. And over dinner, while we were explaining the project, what he did was he ripped out the computer and started to show us places that they can't drive anymore because of the sea level dropping as the land comes up and the ice sheet shrinks, which was just so powerful to me because it was, again, how do we connect to the communities? It's, again, going in, explaining what we think is happening to the natural world, and then listening. Because I don't think I had really believed that we would be able to help with places. It's one of these times where you write a proposal, you think something might be helpful, and it's not till somebody opens up the map and starts pointing to you over dinner that they can't take their boats in there anymore because of the dropping sea level. We'd hope to leverage the work we did here in the Hudson River, where for DEC, we mapped the benthic habitats. And this is basically an example from work that Frank Nietzsche and Bill Ryan, Suzanne Carbot did, where we actually mapped the entire Hudson River from the outer bay all the way to the head of the tide at Troy, where we were actually mapping what the habitats were. And we found oysters, we found rocky habitats, we found sand waves. And the DEC has used these to better understand, be able to manage and better understand the habitats. We're all now much more aware of the oyster habitats in the river. We did not know that the Tappan Zee was covered with oyster beds. And they didn't know that the sturgeon overwintered in these 2-meter tall sediment waves up off of Kingston. So with this knowledge that we could map and understand habitats is why we were hoping in Greenland we could do the same thing, where we could map the habitats and begin to develop a framework that we hope will be useful for understanding how those habitats will change as sea level drops. And this is still a cartoon and not based on our data. We're still literally the data was just collected last week, but everybody's familiar with sort of that walk along a shoreline where you can see at different levels, different types of seaweed, different types of crustaceans growing. That's what we're hoping to map and understand how it's going to change in the future. We're also working with communities, and you might ask, how has this all evolved given the pandemic, and remembering that most of us haven't been able to leave our homes. It turns out that this is actually one of those places where the pandemic has resulted in stronger, deeper partnerships. This is just one of my most recent screenshots. This is terrible. I'm showing a zoom of a zoom, but really this is how a screenshot of our partners in Greenland. This is Carl, Akaluk, and Marina. And because we weren't able to go, Akaluk and to Greenland this summer and do the work with the communities, Akaluk and Marina have taken the lead on it because they began to understand this concept that if we're going to work with communities, you have to go to the community first with your blank piece of paper. So they did the work in both Nuuk, the capital, and Asiat, that second community on the West Coast. And then we went and talked to government officials, elected officials, hunters and fishers, and with schools. And it's been one of those most beautiful moments where you realize that by saying we can't do this, but this is how the experiment is supposed to go, they become so deeply engaged and coming back from the communities and saying, we have to figure out how to get more science into these communities. This is last week in Nuuk at Carl and Akaluk's children's schools, where instead of us installing the tide gauges, the students had a competition to design the tide gauge. And this is Akaluk and Marina and Carl showing us the pictures and describing that this was part of the winning design from the students, that they actually had the innovative concept of adding a piece of concrete to be able to pull the tide gauge down. So we've also managed, so that's been a simple, it's been a very positive outcome of the pandemic, is that it has allowed us to to build a more strong partnership with our Greenlandic collaborators. We did mapping this summer. We went ahead, even though none of us could travel. Again, this was something that turned out to be a beautiful outcome of the pandemic. And here we have two young Greenlandic women working on their masters in geosciences who are actually mapping around their communities. Again, Jane and Nimi, one of whom grew up in Asiat and actually went and they talked to their family about what they were doing, about how they were mapping the depths. And again, here's some of the pictures of the habitats that we're mapping. You can see they're different than the Hudson. But again, this is one of those outcomes of the pandemic that is building stronger relationships and, I hope, building a new model for how we think about working collaboratively with partners and communities. Just thought I'd end here and with a picture of in Greenlandic. This is one of the walls in the Greenlandic Institute of Natural Resources, which in Greenlandic has I want to learn. And I think it's one of the beautiful things about this project is that we really are moving forward where, because of this deepened collaboration, we're seeing more of our materials being translated into Greenlandic, more student involvement and community involvement at a level that we hadn't thought was possible. So I think with that, I will stop and open up for questions as I did. Thank you very much for having me today. If I gave you a whirlwind ride from Antarctica to Greenland.
Thank you very much, Robin. That was fascinating, rather Great, you covered both poles there. Can you pronounce that word?
Nope. You just say every single word. It's Pases Aqua Ursa Punga. You say every single letter, and then I'm sure I'm saying it wrong. I will work on it. I should work on it. That is a good challenge.
Do we have any questions from anyone in the community?
Stop share.
Give it a minute, sometimes people are stumbling to unmute.
Thanks, Robin. Really nice talk.
Thanks.
I have a question for Robin.
I was thinking, Alec, I have all people here who've worked so closely with community. I was thinking Lex is the one who, if I want to have a conversation about this, he's the one I'd like to hear from.
No, it certainly drew me to your talk, Robin. The question I have is how you picked an area where sea level is dropping rather than rising, and what do you think you've learned here that would be relevant if you do a project of this type in a rising sea level area? What would be similar? What would be different?
Well, I think, first of all, sort of how we got here, I think it's a really important lesson, especially for early career scientists, is we got here because Kirsty Tinto was invited to go to Greenland by NSF to work collaboratively with communities. So to me, the huge lesson there is if NSF asks you to be engaged in something like that, you should certainly step forward and take advantage of it. So we picked where someplace was falling because the signal's really big, the data is appropriate, and much of the Arctic is going to have that experience. And it's not something we think about much, right? We think about, we think about our experience where we see sea level rising. So what is applicable? I think what's applicable is that humility and that willing to go to a community with a blank piece of paper. And it's something I would still love to work on, what the best approach is to work collaboratively with communities. Because I think that's what I want to be able to move to other places, is that how is it that you make sure that you talk to the community before you start talking about solutions? And I think that's what I hope will be useful and applicable other places, regardless of this, whether sea level is going up or going down, that we as humans, we in that scientific human interaction space still need to figure out how to do it right. Oh, okay. I see Sasha's question. How have I pushed for these kind of collaborations? Okay, through my role as AGU presidents. One is I've helped structure the new strategic plan at AGU, and it very explicitly calls out that we as a community of scientists should be addressing not just discovery-based science, but we should be embracing solutions-based science because of the, we as a society are facing tremendous challenges. So I've made sure that that's part of it. And I've also made sure that the concept of partnerships is really important, because I don't believe that we as scientists can solve all these issues alone, and that we have to figure out how to work more collaboratively. And that sea level one is such a clear example. What should communities be planning on? What number should they be looking at? Should Greenland be planning on that 2 meter number that DeConto and Pollard have? No, they're not going to see sea level rise. Anyway, so that's my So let's next I'm going to get to Sasha's second question, which is incorporation of indigenous knowledge. I think the hurdles are our community understanding how to, or developing a way to be respectful of indigenous knowledge and understanding the tremendous depth of resources that are out there on co-production. So I think those are the hurdles. I think it's us as an earth science community knowing that there's a lot of work that's been done on that and learning how to. And I'm the first one to admit it. You know, I've worked in Antarctica and where I was able to blithely ignore any residents or indigenous knowledge. And now I feel like that's a very important thing to address. And Lex says, do we have any trained economists? No, not, I don't have any, we don't have any trained economists right now in this.
Do we have any other questions?
Hi, can you hear me? David here.
Yep.
Hi, Robin. Enjoyed your talk. I had a question. So, in Antarctica and Greenland, if Antarctica was to get ahead of Greenland and melt more, would it imply sea level rise for Greenland?
Not in the net. I mean, it would. I don't think you saw that those were Greenland focus numbers you saw, and you saw that the signal by 2100 in most places in Greenland would overcome much that we'd expect from Antarctica.
Okay.
So not yet, maybe by 2200. And I think that's, you know, that's the beauty of having gone in and focused on Greenland, is that there, at least for the next decades, it's going to be Greenland focused and the physical processes that are happening immediately at Greenland. Lex, that's another nice reason that we focused on Greenland, was that the signals are large, and what we learn there can be applied elsewhere.
So I know much less about Greenland than I do Antarctica. I was wondering if you could speak a bit about are the projections for Greenland much better constrained than Antarctica?
Are they better constrained? Probably. Yeah, I don't think, because we don't, okay, yes, because you don't have the wild swings of that are introduced by the ice shelves, right? Mm. You have fewer, I mean, Greenland could also benefit from some of the improvements in how you deal with ice sheet models, particularly the base, since it has a highly variable, it has tremendous variation in basal heat flow, but you don't have the same wild cards of the ice shelves that you do in Antarctica. Mm-hmm. And it's going to put, you know, Greenland's going to pull itself out of the ocean pretty quickly. At least that's the way I think of it.
Okay, it's just turned 12 o'clock. Does anybody have any further questions?
Alrighty, thank you very much, Craig.
So, thank you very much for giving a really interesting talk. I should have asked you earlier, but so we record these. Yeah. Do you mind if I put this online?
That's okay. I don't think I said anything. Maybe I shouldn't have told the snowflake and the vegetable story, but whatever.
I don't think that's in the recording.
Good.
But I wish that's a great story. Thanks again, Robin.
All righty.
thank you everyone for joining us. I hope you have a great rest of the day.
Alrighty, thanks, Greg. Bye-bye.
Cheers. Bye, everyone.